Welcome back, guys. My name is Abraham. For those who are new to this channel, I'm a BCom Computer Science and Information Systems student at Nelson Mandela University. So it's been so long since I've made some video, and then as you can see, there's some change for those who have been up with this channel for some time. I used to use like a circular thing, so now I'm like in more of like a rectangle thing. But otherwise, let's jump to the main purpose of this video. So today we're going to be dealing with something called trees. So in data structure, we do have our very special data structure called trees. So we do have binary trees and binary search trees. We're going to be focused on the two, and then I'm going to try by all means to make you understand what is actually happening. So this video will be basically about the theory side of these data structures, and I won't be diving deep into building the code or writing the code. We'll be doing that probably in the next video, but this video is basically about that. Now, as you can see, we do have some circles. So those who are new to data structures, they might be questioning one of these things. So this circle is being considered to be a node. It's more of like a container that stores information. It can be a text, can be your name, it can be the other person's name. But in the demonstration of this video, I'm gonna be explaining this thing through a tree. So as you can see, this thing is being called a tree, and then a trees have what? They have a root, they have children, right? So same applies to this thing. So this thing is considered to be a root, and then these are children. Let me take you through your family members. This is being considered to be a parent. Your father can have what? 2 children. Same applies to your father's children. They can have what? Other children. So as you can see, it's more of like a generational tree. It makes sense, right? So let's move on to the next part. We do have a binary tree, we do have a binary search tree. What is the difference? The difference is binary tree is more focused on ensuring that the nodes or a parent or a root has 2 children. It's about balancing the tree. It doesn't care much about the order of the children within the nodes. While on the binary search tree, when you structure your tree, you have to make sure they are put in order. Meaning, if this thing, it is 5, a value that is to be stored within this node on the left should be less or equals to this value. And then the value to be stored on the right side of this node is to be a value that is greater than the one that is within this thing. Numbers are better, are a good example in this situation. So in a binary search tree, we can have values like 5, 4, and less. And then while on the other side, we can have values like what? 6 and upwards. So let me just say 6. So now we do understand the logic behind binary search tree and binary trees. Let me explain something about data structures for those who don't even know what data structure is. So break this thing into 2 parts. We do have data, and then we have structure. So data is being considered to be more of like an information. This is where it's like, it can be any form of data type. It can be your name. Your name is also data. It can be your age. It can be anything. Anything is basically data. Then we have structure. So structure is more of like putting things in a specific way, order. Within computers do have memory, right? Then data structures are more concerned to make sure that we store information in a particular order within our computer. Okay, now let's move on. As we have said, this thing, a node that contains nodes below it, or that is pointing to other nodes, it is being considered to be a parent, if that makes sense. So what I'm saying is that this thing, it is considered to be what? A parent, and then this thing is being considered to be what? Child. Same applies to this one. So we have a parent, we have a child, right? So the next thing is, how do we add on a binary tree? So let's focus firstly on the binary tree. I'm going to be focusing on the adding part. So as I've said, on binary tree, we don't care much about the order. All we have to do is to make sure that what our nodes are being balanced, right? We're going to start from the left to the right, meaning if we were to traverse through this tree or go through this tree, we have to ensure that what we always balance. So now let's start this thing from the scratch. We build our own trees to make you understand what is actually happening. I'm going to create my first node. This is my node. The first node within a tree is being considered to be the root. So I'm going to label it to be root. And then we have what? Let me copy this thing, put it here. We have child. I'm gonna copy this thing. We have a child, and so on. So when we insert, we always start in the left. So since there is not, when we start at the beginning, when we create our binary tree, it is empty. The first node that we insert or we create, it is called the root, right? And then with binary trees, a node, the circle, it has 2 pointers. It has 2 arrows. There's an arrow here. It also has arrow here, on which is to point where? Is to point to the children. It doesn't have 3. It always has 2. So now we're gonna be adding our children. So we're gonna be adding our first kid, our first child here. And then we're going to move on and add our another child here. So when we add, we always start at the left, meaning we're going to check if this thing, the left pointer of this root or node is null or what. If there's something, we're going to add. If there's nothing, we're going to add to the left. But if there's something here, we're going to add to the right, or we're going to check if there's something on the right. How that one makes sense? And then if we want to insert another node, we're gonna copy this thing, and then what we're gonna do is we're gonna check from the left hand side, do we have something? And then we're gonna figure out there's something. Then we come to the right hand side, do we have something? And then we figure out there's something. Then we come to this one, do we have something on the left? We figure out there is nothing on the left. Then we do what? We come and make this one point to what? We make this one point to this thing. This is how we insert. Same thing if we want to insert again. We're going to come here, check if there's something to the left, there's something. Something to the right, there's something. Something to the left, there's something. Something to the right, nothing. Then we do what? We bring it here. We point. This is how we build a binary search tree. Binary tree. But with binary search tree, this is how it's going to be like. So at first, we're going to be creating our node on which you do it. The best way to demonstrate this one is by using numbers. So let's say our first node contains a value of what? Of 5. And then our next node contains a value of what? Of 6. So as I've said, this thing is more focused on what? On ordering the things that are being put. It's about placing things in order. And then as I've said, values that are less or equals to this root or the parent, they are being put to the left side, and then those greater than what? The parent or root are being put at the right hand side of the thing. Okay, so now we have 6. So we check the value of this thing. So we compare the value of this, and then check which direction should we place this thing. Then we realize this thing should be placed at the right side of this thing, since it's bigger than this. No problem. So now we check if this thing is pointing to anything, only to realize, okay, this thing is what? It's pointing to nothing. Then we take this thing and then we put it here. Then we have another value by the value of what? Of 2. We come here, we start here at first, we check, is this value greater than this value? Then we realize no, this value is less than this value. Then we do what? We check if the left side of this thing is pointing to something. And then we realize what? This thing is pointing to nothing. We take this value, we put it here. If we want to insert another value, let's say 10, what do? So same thing, we create our node here, 10, then we check, okay, is this node greater than this? And then we realize it's true. Then we check, is there something on the right side of this thing? Only to figure out that there is something. Then we go and come here. Then we check, is this value greater than this value? No. So that means we should insert what? On the right side of this node. And then we check if this side there's something. And then we realize there's nothing. Then we take this value and then put it here. Then we want to insert a value of, okay, let's make this thing 7 so that you understand. So we create another node called 6. So now we check, is 6 greater than 5? Yes. Then we come here, is 6 greater than 7? No. So then what? We check to the left if there's something to the left. And then there's nothing, since it's pointing to nothing. Then we put it here. So basically this is how we build our binary search tree. The first demonstration was how to build your binary tree. Then now we move to the binary search tree. When we build trees, we do have certain things called levels. I'm not so sure if this thing is gonna be well. So we do have levels. Can I put it to the back? Send backwards. Okay, send forward. I don't know how this thing works. Bring forward. Bring forward. I absolutely have no idea how this thing works. Send to front. To front, to back. Oh, yeah. Finally. So, this thing, it is being considered to be what? Can I label this? Okay, let me just use a text. Okay, can I use a text here? Okay, it's called what? 11. And then same applies to this thing. To back. Also, this thing is called what? 11. So basically, this row, it is being called a level when we deal with binary trees, the binary search trees, or trees in overall. And then also this thing is being considered to be a level. So those are like some of the things, probably when you go through an interview, those are some of the things they might be like, identify the levels within your trees. So, and then also they might ask you, what is your, when you, especially on trees, they might ask you, show me one of the parents within the tree, on which it is best that you know that anything that has children, it is being considered to be a parent. And then they might be like, show us a root. A root is the starting point of the tree. So this has been considered to be root, and then this is a parent. This is a parent since it contains what? A children. This is not a parent since it doesn't have children. So what is the next thing? The next thing could be when they, it could be it could be the height. Yeah, could be the height of the tree. So what is the height of the tree? So the height of the tree, it is being considered straight from the bottom. So it's what? It's 1, it's 2, it's 3. It's like you start from the bottom, then you calculate. Then you realize that the height of your tree is 3. Oh, actually, let's check that one up pretty fast. I should be able to see it. binary tree. Let me just say binary tree. So height is 3. So it's 1, 2, 3. Yeah, this is basically how you calculate height. So you say 1, 2, 3, and then a degree. You start here. You start at 0. It's like different. So it's 0, 1, 2. So the degree of this thing, it is what? It is 0, 1, 2. So those are some of the things you need to know when you deal with some trees. So let's delete a node. This is like the trickiest part about trees. So we do have, I know, let's try to delete this node. If you want to delete this node, we're just going to check, hey, where is 2 from here? We realize this is 5, that means it must be on the left. And then we get to the point where like there's 2. But before we delete this thing, we must check if this 2 is pointing to other stuff. Because, let me show you an example. If we delete 2 and then we realize, only to find out that 2 is pointing to other things. Let me show you. This can be something like this. I have to change this thing so that, oh no, I have to move it a bit here. Move this thing something like this so that I can, yeah, point this to this and then point this to this. So if we want to delete 2, let me put it here. It should be on the same level. So I'm gonna pull this here, pull this here, pull this down, pull this down, pull it here. Yeah. So hiding, I'm blocking my. Okay, let me try to do this. Yeah, you can see. Okay, so if you want to delete if I want to delete 2, okay, let me change this to 3 and then change this to 1. So if I want to delete 2, I should always ensure that I check whether 2 has children, because if I delete 2, I won't be able to access this thing, because from 2 I can access this and access this thing. But if I just delete 2 in overall, meaning I'm saying this thing is no longer pointing to this thing, that means I won't be able to access all the nodes, all these 3 nodes anymore, and it's a bad thing. So the best way, when you delete any node, you need to ensure if there are any children, if that makes sense. And then if there are children, that means you need what? You need to reorder your tree, because this is a binary search tree. You need to always make sure that it's in order. Let's go back to this example. If we want to delete this thing, what is the best way to delete this thing? Remember something. 3 is bigger than this, and then 1 is smaller than 3. So to delete this thing, how do we do it? So we take the value that is greater than this, and then we put it here, meaning this thing is going to be 3, and this thing is going to be 2. And then we do what? We delete this, then our tree is ordered again. That is pretty simple, right? Let's go back to this thing. If we want to delete 7, what do? We check if 7 has any children within that are pointing to, and then only to find out there are children, right? So how do we delete it? We take 7, we put it here, right? We put 10, we put it here, and then what? We delete this. Then there won't be, this thing won't be. This is how we basically do the operation, if that makes sense. Wait, do we have to wait? So do we have to go all the way to this point? Because if our error, this means it can be something like this. Need to check that one. Deleting. In binary search. Let's figure out that one out. We do. I know we do have success in all those things. So valid binary search tree. In the above base tree, if you want to delete 17, now that one is pretty simple. I want to delete a value that is least bit. We're going to delete 8. Okay, yeah. Can we delete? Let me see if I can find a perfect one. Okay, this one is more interested on the code. Okay, let's just pick A. So in the above our binary search tree, if we want to delete 8, on which this is our value, then we will replace it with 10 and remove 10, or copy 10 to 8 and remove 10. So basically what we're doing is that we're saying 8, no. Oh, we appreciate the dudes who have done this thing. So what they're doing actually is that they say 8, I'm not so sure if you can see. Let me try to zoom in so that you can all see. Oh, no. Can you all see? Okay, yeah. So when we want to delete this thing, we take this thing, we put it here, right? And then we take 10, we put it here. And then we delete it. So as you can see, 10 is here. Our binary, how I was explaining this thing was, right? Now I'm questioning, like for example, if I want to delete this 18, right? How am I going to do it? Oh, no, I think I was wrong about something though. As you can, I'm not so sure if this is a must, but when you play, so this is how values that are greater or equals to this value are being placed on the right. And then what I said was that the values that are less or equals to this number, they are being placed on the left. But in this situation, we see something different. Okay, so now I'm more interested on this one, where I'm trying to. Okay, let me see if they can give me an example. Can you all see? Let me try to zoom in more. Okay, so what is happening is delete node. Okay, I feel like this one is good. Delete node 85. So if you want to delete node 85, this will just be easy. We just remove it. That's it. Delete node 12. Delete a node on which is greater than this one. Let's see what's going to happen. Can we delete 60 here? I mean 60, because 70 is, yeah, something like that. Can we delete such? Delete 50. If we delete 50, that means we what? Replace 50 with in order success. That means we're going to try and figure out this one is the smallest. And then from then what? 60, 75, and then 52. Yeah, it makes sense, because okay, if we exchange 50 with 52, right? And then we try to navigate it to the right position, only to figure out that this is where it is supposed to be. Because if however this thing was maybe 40, then 40 was going to be here, and then push 52 to this place. This is basically now they're explaining some code. So I'm not so sure if this is a part of a copyright, but all I'm saying is that I don't know how to appreciate. This is how much I don't know what to say in terms of avoiding this thing of copyright, because I once opened a channel and then they hit me with this thing of a copyright. But otherwise, I feel like that's more of understanding binary search tree. So when you delete or delete any node, you have to structure it, put it in order again, if that makes sense. So yeah, so what from that thing we could have learned that if we want to delete 5, the best thing to do is what? Take this 5, put it here, meaning this thing becomes 6, this thing becomes 5, and then we delete this thing. So my advice to anyone who's trying to learn data structures, the best way is to understand the theory before you write code, because code is basically your information or your knowledge towards something. So if you don't understand it, you probably cannot code it. Otherwise, thank you guys for watching this video. Don't forget to like, subscribe and share. Basically, I'm building this channel just to expose my knowledge, and then yeah, I just enjoy. It's more of like building my portfolio. Anyways, thank you for watching. See you in the next upcoming videos. Cheers.